Hello, welcome to another video in the Big O notation series. And in this video, we want to explore the O log n, which is the logarithmic time complexity. In the previous video, we talked about the constant time, which is the O of 1, and we also explore the Big O complexity chart where we see the performance of O of 1. So before we go on, if this is your first time coming to this channel, ensure you subscribe, like, and share. And make sure you set the notification for this channel so that you keep on getting new videos when it's being uploaded. So let us go to the business of the day. What is O log n? O log n algorithm running time increases logarithmically with the input size. Logarithmic time complexity usually apply to algorithms that divide problem in half every time. I want you to take note of this, this is the foundation of the O log n. Algorithms that divide problem in half every time, meaning the runtime barely increases as you exponentially increase the input. What are the example of O log n in real life, right? The first example is searching for a word or finding a word in dictionary. Let's take an example whereby you want to find a word that starts with X. For example, we want to find a word like secondary or senior in a dictionary. The first thing you will do is to open the dictionary in two parts, the left hand part and the right hand part. Now, you want to check, do I have X in the left part or the right part? If there is S in the right part, you abandon the left part. Okay, so that fashion continues until you achieve what you're looking for. Another example is searching your contact details for a phone number. So you search for related words and the algorithm behind the scene filters the contact that look almost the same as what you are typing. There is another example which is binary search in programming, and we are going to consider the visual representation of binary search. But let us look at a little example which I have drawn out. You can look at this list. So let us take this as an array, right? We have an array that has 12 numbers. And in this number, we want to search for a particular number, and that number is our target. So the target is 21, right? So the first thing we want to do is using the algorithm, which is the O log n, we want to divide the array into two. And when we divide it into two, right? So we want to check, do we have 21 in the right hand part of the array or the left part of the array? If we have 21 in the right part of the array, then we need to abandon the left part of the array. So now we continue in that same fashion to explore the new right part of the array. So we need to also divide this into two and check, do we have 21 in the right or the left part? If we have it in the right part, we pick the right part and move on. If we have it in the left part, we do the same thing, we pick it and move on. But if we don't have it in the left part, what should we do? We should abandon the left part. So now we have 21 at this position, which is the right part. So we also want to dig deep in the right part. Do we have 21 in the right part, or is 21 the exact number at the position of division? So this is where we find our target. So the algorithm here is O log n, which is the logarithmic time complexity. You can see the array is being divided into two at every process. That is why you see logarithmic time complexity usually apply to algorithms that divide problems in half every time. So let us look at the big O complexity chart so that we can understand the performance of O log n. If you look at the chart, you will see we have the green part. This is excellent, and that one is O of 1. But there's another one that is lighter green, right? This is O log n, right? So it's close to O of 1. It's almost constant time. It's a very good algorithm. All right. So at this point, you can see when you input large data, right? It's going to break that data into two and it continue in a very good fashion until your target is achieved. Let us look at more visual representation. Okay, we have a very large array here and we want to search for a particular number in this array. Now we have linear search, right? We'll get there. In linear search, right, when you input a particular number, let me say, for example, we want to search for the number 171. Okay, let us see it in action. And I click on search. You can see it starts from the beginning. It will move from beginning until that number is seen. So it's comparing every number. You can see every number at a particular index will be compared until the result is found. So meaning this process, right? To see this number now, we have taken how many process? You can see the process here. This is 7 process, or let my minus the 0. This is 6 process. So it took 6 process using a linear search to get to 171 at index 7. Now let us explore the binary search, which is the O log n. You can see the first thing it does is to divide the array into two. At every operation, the array will be divided into two. Now it has divided into two, and with just 2 steps, we found what we are looking for. So just imagine we are searching for a number, right, which is 510. If we are searching for 510 using a linear search, you can see the process is going to be 15 times just to get to the index 15, right? So you can see it comparing every number at a particular position. This is linear search and we're going to get there. We're going to write an algorithm for this, but I'm just doing this for you so that you can know the difference between a linear search and a binary search. And the binary search is O log n. You can see this is what 15 steps to find the number 510. Now let us compare that with the binary search. Remember, the first thing it does is to divide every operation by half. You can see with just only one step, we've gotten what we are looking for. So this is the importance of binary search. So now, the next thing we want to do is to consider some code example of O log n. I'm currently on my VS Code and you can see I have created a new file, which is the big O of log n. Now, the first example I want to give is the binary search, which is the operation that is being used for this search. So let me write the code. So the first thing I will do is to create my function. So I'm going to call the name of my function binary search. And it's going to take 2 inputs. One is the array and one is the target. And the other is the target. Okay, so the first thing I want to do is to set the left and right point. So my left is going to be 0 and my right is going to be the length of the array. Now I want to loop through the array and get half of that array at every step. So what I'm going to check why the left is less than or equal to the right. Okay. So why left is less than or equal to the right, I'm going to set a variable called mid, which is the middle, right? And the middle is going to be left plus right. Left plus right. I'm going to divide it by 2. Now, the next thing I want to do is to access every element by the index. So I want to check if the array, okay, if the array of the mid, which is the mid, right, is equals to the target. That means I have found what I am looking for. So all I need to do is to return the index. Then else I want to check the array using the mid position. Okay, so I want to check if the array at this position is less than the target. Then I want to increase the left part by 1. Okay, so I'm going to do left plus equals to 1. Then else I should decrease the right part by 1. Okay, so the right is going to be mid minus 1. So basically this right is not actually decreasing by 1. It's setting the new position as the mid position but minus 1. All right, so we're going to see it in action. I'm going to run in the debug mode so that we can see it in action. So but however, if all this process is being run and we do not find anything, so we want to return minus 1, meaning the target is not in the list. Okay, so let me define some variable at the bottom and we should invoke this function. So I'm going to create an array with 1, 3, 7, okay, 5, 7, 8, 9, 10, 11, 12. Now I want to set my target. So the target is 3. Okay. Now let me invoke this function and pass in this value. So I'm going to invoke that function and pass in the array and the target. Okay. So what I want to do is to print out the result so that we can see. All right. So let me run this program. You can see it says my target exists index 1 and obviously is correct. You can see it exists what? It index 1. Let me pass in another value. I'm going to pass in 11. I'm going to save and run. My target exists at index 7. All right, so let me run this in debug mode so that we can understand what is going on. So I put my breakpoint and I want to run in debug mode. Okay, so I'm using F11, right, to move over. So you can see we now have an array, right? We have an array. This is the array. We have our left and we have the target. So we have the left, we have the mid, we have the right, and we have the target. So I'm using F11 to go through the code. So you can see at this point, right, we are checking if the array at that position, right, is equal to the target. Right. So you can check what is this. You can see this is what the mid is 4. Okay. So I'm going to use F11 to move to next step. So since it's not, then we'll move to the next step and we want to compare if the array at this position at index 4 is less than the target. Okay. What we want to do here is to increment the left by 1. And you can see the left is now 1. You can see the highlight. You can see when I hover on it, you can see the value inside is now 1. So the process continues since left is less than or equal to 9. Left is 1, 9 is right is 9. So that process continues. It half the value of the array at every time. So formerly the mid was 4, and if I move one step further, you can see the new mid is now 5. So this process continues until the target is found. And you can see the target is what? Found. So the takeaway here is logarithmic time complexity usually apply to algorithm that divide problem in half every time. Alright guys, I hope you find this helpful. So thank you very much for watching. I'll see you in another video.